benefits of feed forward to make some systems that really, really respond well. Well, I want to review the PI controller. Yesterday, Richard talked about this in the context of the PID controller. In most cases, for motor control, we don't use the D term, especially if we're using cascaded design techniques. And I'll tell you what that is in just a minute. But in most cases, what we have is we have a situation where we have an integrator and a steady state gain in the same topology right here. We have a commanded value, a measured value. We generate the error signal. The error signal is split up into two paths, straight gain, and then this is integrated with an integrator gain, and then the outputs are combined. Now, this is the parallel PI control topology. This is the one that I think most people are familiar with. Just because it's intuitive, you can actually see what's going on here. And if you look at the transfer function of this particular system, it looks something like this. So if I adjust the KP term, what it does is it adjusts this level right here of the Bode plot. And if I leave my I term the same, what it's also going to do is adjust the controller 0. Because obviously the higher this gets, it's going to intersect at a different frequency. So as this term goes up, the controller 0 is going down. Now, if I adjust the I term and leave the P term alone, it's going to be adjusted like this, and that's going to cause the controller 0 to go up. So what we see is this frequency right here is actually a function of both the KP and the KI terms. Well, this 0 is actually very important to us because when you're designing a PI current controller, for example, where we set that 0, we would like to be able to do it so that we get pole 0 cancellation in our closed loop frequency response. So having this adjusted independently can all of a sudden start shifting our 0 and throw off our frequency response. That's why a lot of people prefer to use what's called the series PI control topology. Has anybody seen this one or used this one before? A few people have. Okay. Now, in this case, the error signal comes in. The first thing that happens, it gets multiplied by a steady gain, which is called Ka, and then that gets fed forward to the output, but it also goes through the integrator, and then they're recombined like that. Now, if you look at the Bode plot, if you look at the frequency response, exactly the same frequency response. We haven't changed that. And you can actually relate the series form of the PI controller to the parallel form as shown here. So I can derive one from the other. So why would I want to use a series PI controller versus a parallel one? The answer to that question is because now I directly control the 0. I have independent control of where that 0 is. And that's going to be a benefit to me as we get into designing the as we design current loop controllers. So in this case right here, Ka is going to adjust the amplitude not of just this portion of the graph, but the entire graph. That's the nice thing about it too, because this is now in series with my total gain in my system. So when I bring that up, everything else in the loop that's part of that closed loop gain will also go up. It's not just adjusting one part of it. And then KB is the 0. It's exactly equal to the 0. So I can set that independently wherever I want that to be.